Today we're going to go over GibbsCAM and VoluMill for GibbsCAM. A little bit about VoluMill before we begin. VoluMill is actually a third-party application. It's developed by a company called Solarative Technologies, and it has some unique properties that I'll talk about here in just a little bit. However, this module, although third-party, works directly within GibbsCAM just as any other process does, and again I'll be showing you some of that here shortly. Let's go ahead and start with this part. The part I have here is aluminum, call it aluminum 6061, and you can see that it's an open pocket, that is, it's open at one side. Later on we'll go ahead and look at another example, which is a completely enclosed pocket, but VoluMill works equally well for both types of situations. Over here on the right in my operation area, you'll notice that I have two operations. I have a traditional rough, and then I also have a VoluMill rough. And I have both of these here. This would not be a real world thing, but I have both of these here just for comparison. Before we begin, let me go ahead and point something out here. I'm going to pull up the operation summary, and I'll show you how we calculate all this, but you'll notice that the run time for the traditional rough is, in this case, 2 minutes 31 seconds versus 52 seconds for the VoluMill. So it's not unusual at all to get 2, 3 times, even up to 8 times and greater efficiencies with VoluMill than you will with traditional roughing, and I'll be explaining why here in just a second. I'm going to go ahead and minimize GibbsCAM right now, and I'm going to bring up one other application. And this is our milling advisor. Now this is a free download. You can download this on www.VoluMill.com. And the reason I have this application here is because it's the only one I know of that has an entry for VoluMill for calculating feeds and speeds, as well as for traditional types of machining. So I use this to get the feeds and speeds that I plug into both the traditional roughing and the VoluMill itself. Now, one other thing I'd like to say here is that if you did not have this milling advisor, you could go ahead and follow some guidelines for using VoluMill, which is for any particular tool, you look at your tooling supplier's recommended IPT, feed per tooth. You go ahead and stick with that, whatever number that they normally do. However, on the SFM, or the surface feet per minute, you want to double or even triple that number to get to the feeds and speeds that you want. So again, if I didn't have this milling advisor, I'd still be able to go and plug in some numbers that are close for use in VoluMill. So having said all this, let's open up the traditional rough, and I'm just going to show you how I arrived at those numbers. If I go to heavy roughing, and I had mentioned we're using aluminum here, 6061, you'll notice that 6061 is here in the list on our calculator, and we're using a 1/2 inch tool, carbide with 3 flutes, and this is going to be a 1 inch deep cut, so that's 2 times the diameter, so I'll leave that there. We're going to go ahead and say it's uncoated. If we go to coated, we can actually go to greater feed rates, but we're going to kind of go middle of the road here. We'll say it's heavy roughing. We're going to say that the tool holding is very good, so it's not going to fly out or anything. And then the maximum speed of our machine is 12,000 RPM, and the maximum IPM is 800 inches per minute. That's as fast as it can go in a straight line in a G1 move. Now, the reason we plug this in is that when you go into VoluMill, it actually, once it gets past the initial rapid planes, it will not use G0. It will not use rapids. It actually uses G1 for the rapid moves. And the reason for that is when you use G0, it won't necessarily follow the path that you have. It'll simply go from point A to point B as fast as it can. So in order to ensure that the paths are followed, we use G1s instead of G0 in the VoluMill calculations and in the posted toolpath. Now, if you look down here, we have a conservative and aggressive column. So we're going to go ahead and run with the conservative column for this particular example. And for heavy roughing, you can see that these numbers match, right? The RPM 11,001, 11,001, and that sort of thing. So I plugged in these numbers directly from those two to go ahead and get that. Now, if I now switch the calculator to VoluMill, and I open up the VoluMill process, we can see that, hey, we've maxed out at 12,000 here. So actually, if we had a faster machine, we could do even better than we're doing here. But the thing I want to point out is, look how much faster we're going in IPM, 534 inches per minute, which is the same value that we have plugged in here. So this is not unusual at all. So the SFM, you notice it's 1571 instead of in the 500 surface feet per minute that we normally see for this type of material. So how does VoluMill do all this? First of all, let's go ahead and calculate this, just so you get a feel for what this looks like. Okay, and there's the actual calculation time. And I want to point out one other thing. Let's go back to the traditional roughing. Now, traditionally, roughing up until this point is geometry driven. What I mean by geometry driven is, if we look at the general shape here, what we've done to generate the tool path is simply to keep offsetting that shape until it collapses in on itself, or in this particular case, since we have an island, until it meets an island and they kind of morph between these two shapes. But it's all driven by the geometry. It's not really driven by machining at all. Now let's look at the VoluMill toolpath, and you'll notice it looks different, right? We've got loops. You'll notice also there's no sharp edges, so it never slams in to a corner. It never goes and all of a sudden takes a right turn. Everything's very smooth. Everything's radius. Okay. What VoluMill does is it sets a volumetric removal rate, that is cubic inches per second of chips flying out of the machine, and it tries to maintain that constant volumetric removal rate. And so that's one thing that it does. Now, this is much more advanced than some other high-speed roughing algorithms that are available today, in that most of them use what's called 2D tool engagement. That is, they look at the tool, which is a circle, and they say, okay, of that tool, we only want to have this much angular engagement. So it's in a 2D approximation of maintaining a load on a tool. This is actually monitoring the 3D removal rate. So it's quite a departure from that kind of philosophy. Another thing, and this is a patented algorithm, by the way. This company developed this algorithm themselves. So that means is that it uses very unique technology. But one of the other things, and we'll actually see it here in just a second, one of the other things it does is use a slotting kind of approach. So in this particular part, when we start to get into it a little bit, it has to get into areas where, you know, we're not really starting from the outside. So it'll create a slot. We can kind of see one right here. It'll create a slot, it'll slow the feed rate down, it'll create this slot, and then grow rapidly from there, go like a bat out of hell from that slot. So that's a very different and unique approach as well. Let's go ahead and take a look at this VoluMill, and I've got this set, by the way, so that it's just displaying the VoluMill and not the traditional roughing. So you can see at the beginning, it's actually, if it's got an open side, it'll come in from that open side and do that. But I'm going to let this run for a little bit. Okay, right here you'll notice that it created that slot that I was talking about, and it actually, you notice it took it out in 2 depths, so it will actually vary the depth, the step over, and the feed rate. So this is very different than what you're used to seeing. When you post-process this code, typically you're going to see feed rate changes on just about every line, and again, that's because it's monitoring that volumetric removal rate as it's going along. So I'm going to go ahead and let this continue on. You'll notice how it loops into those corners, and again, instead of just slamming in, so it'll come in loop, 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 and go and take that out. So another side benefit of this, by the way, is the fact that not only are you removing material faster, but your tool life goes way up. It turns out that in traditional roughing, you're loading and you're unloading that tool a lot, and that's very hard on the tool. So we've actually had some customers purchase GibbsCAM just because of the tool life savings, and nothing else. So that's a little bit on that aluminum open example. Let's move to a different example. Let's go to a little bit harder material, stainless 304. So in this particular case, we actually have a closed pocket here. And as before, I have traditional roughing, and then I also have the VoluMill here. So if we look at the time comparisons, we've got like, we'll call this 45.5 minutes versus about 36 minutes. So, you know, some significant time savings there in this particular example. But one other thing we did different is we've got two processes for each, for the traditional rough and the volumetric rough. So what we're doing here, VoluMill rough rather, but what we're doing here is with the first tool, it's a 1 inch, we go through and we'll leave 1/2 inch of stock, and then we're going to go in with the 1/2 inch and clean up whatever's left. So in both of these cases, we have rest milling going on. So if I look at the second process on the traditional rough, we're doing this by saying, hey, clean up the material that was left with the last one. And with the VoluMill, if I go to the second one, you can see that we're saying clean up after the last tool, which was a 1 inch tool that left 1/2 inch of stock. So that's how the rest milling is accomplished with VoluMill here in this particular case. Okay, again, we see some other things. Just to go back to the milling advisor, let's go and set this to stainless 304, and let's look at the, let's just keep with the 1/2 inch example. So it's 5, this is an inch, 5 flutes, an inch depth of cut, so we're going ahead and keep that in the VoluMill, and you can see that we're going at 98 inches per minute. And again, that's what we already have plugged into here. And we're going to do a helical ramp of 1 degree. And again, those values are plugged in there. 6.5 thousandths or 10 thousandths step over as well. So that's how we just derived all of these numbers right here. Let's go ahead and take a look at this. So you notice that, we slow it down here a little bit. You notice that we have that helical entry to begin with at that 1 degree angle, because we have nowhere to go. So it will never just plunge in. It'll do a helical entry or ramp entry to do this. Now, one other thing I'm going to point out is that when we get to these materials like 304 and harder, instead of, when we build that slot, we're not just going to go straight into the slot as we did in the aluminum. What we'll do is we'll actually do a trochoidal motion to create that slot, so that there's less load on the tool and the harder material. And that's just a switch I set. So you can actually see it. It's building the slot right now, but it's going in a trochoidal or circular like motion, and then once it completes that slot, you don't see it here, but the feed rate goes up, and then it'll go in as far as it can until it needs to build another slot, and then it'll slow down, build that slot, and then go and grow from it. Okay, so now it's making another slot, and then it'll grow from that. Then finally we have the cleanup with the 1/2 inch tool, taking out the 1/2 inch of stock that was left. You see it loop into those corners on the finish right there, looping into those corners. So that's how we'd apply VoluMill in a closed pocket situation with a little bit harder material. Let's go to another example. And so far, in all the examples we've seen, it's been 2.5D, right? Straight pocket that doesn't change. In this particular example, you can see that we have a valve body enclosed in a semi-circular kind of stock there shown in blue, and we want to remove it that way. And again, I have both the traditional rough and the VoluMill here for comparison. If I open the operation summary, here we're starting to see much greater savings, more material to remove in a different kind of situation, which is not straight 2.5D. So in this case, we're about 5 times faster, 68 minutes in traditional rough versus 14 minutes in VoluMill, 5 times faster than traditional roughing, and these are not unusual numbers to see in cases such as this. If I open up the VoluMill just to see if we're on track with everything, half inch, 5, so 98.2 IPM. Okay, and again, we can go even faster. We can tweak that to be faster, which I'll talk about in a second. So we could actually, go to the more aggressive numbers and plug those in instead. That's one approach to take. It's just to go to the top end of this if we want to, tweak it even farther than what we see here. Okay? But one other thing I want to point out, let's look at the traditional roughing first, is that what we want to do in a case like this is we want to leave like a 0.1 100,000th stair step. That is, when you rough out a core like this, you're going to have kind of the wedding cake effect, and we want the steps of those wedding cake to be no more than 0.1. So in traditional roughing, what I do is simply say, hey, I want a Z step of 0.1 in order to maintain that stair step. In VoluMill, you take a different approach. So open this up. You go and calculate, or specify rather, a ridge height. So I've got ridge height clicked on, and I say 0.1. Notice I say cut after lower depth. So what it will do is we'll see here when I run this, let me rewind that and slow it down a bit, is you can see that it's taking some pretty hefty cuts, 1-inch cuts with a 1/2-inch end mill. Right? And it's coming in from the outside as much as it can, which is good. And there's another cut. And now you'll see on this cut in particular, when it's done, it's going to go back from the bottom up and put in that 0.1 ridge height that we specified. And there's the finished product. Now, you can actually get more aggressive with what you see here. One way is what I've already specified, going back to the milling advisor and picking the aggressive column, but there's also a feature here called chip control. So I'm going to go ahead and specify this, and let me touch on this question mark for just a second, because it brings up some graphics that I'd like to talk about. So your tooling supplier talks about feet per tooth or inch per tooth. What they mean is that this is the feet per tooth when the cut width is greater than or equal to 50% of the tool diameter. Okay, that's a worst case scenario. But when you get into harder materials like 304 and above, we're actually not taking anywhere near 50% typically, and so the actual IPT is going to be much less than that. So you're saying that the maximum chip thickness is only equal to 60% of the IPT at 10% of the cut width. Okay, so we can leverage that fact here in the chip control. Okay, so what we're saying here is that we're going to calculate the feed, and we can see the chip thickness and the IPT displayed here, and we have a step over of 0.065, which is typical for the initial state of this. However, we can go on and play with this value a little bit. Notice the material removal rate is 6.37 and the IPT is 98. Okay, so let's make note of that. Let's just say I'm going to go to 0.13. So I'm going to double the step over. You notice that the material removal rate went up, but yet the IPM went down, okay, in order to compensate for that. If we go ahead and apply those parameters and we redo this, you'll notice that the toolpath looks a little bit different. It's a little less sparse. If we go to the operation summary, we've now gone down to 11 minutes versus the 14 minutes that we had there before. So we've got even greater savings in time that we did before. But one thing I want to go back to this and say, this should be rooted in reality. And by that I mean that for every company, for every different company, in fact, even for different machines within the company, you're going to want to do a little homework when you implement VoluMill. You're going to want to take the default conservative values from something like the Milling Advisor or the guidelines I gave you previously and run that. But then you want to always push it a little bit more. You want to tweak it a little bit more so that you have good feeds and speeds numbers for that particular machine. Obviously, if you have a weaker machine, it might not be able to handle a cut width of 0.13 on a ½ inch, but if you went to another machine with greater horsepower, that would be no problem. So you do actually have to take full advantage of VoluMill. You do have to do a little bit of homework, a little bit of tweaking of your feeds and speeds in order to obtain the maximum value from VoluMill. Okay, so that's the end of my demonstration. Just in summary here, then we've looked at VoluMill running inside of GibbsCAM. An obvious advantage of VoluMill is that it will remove material a lot faster than traditional roughing algorithms and approaches. A side benefit of VoluMill is that your tool life will typically go way up because you're not constantly loading and unloading the tool as you do in a traditional roughing approach. Thank you very much for your time.